All right, so welcome back for section 10.1, part 2. We're doing hypothesis testing on a population correlation coefficient. Right? All right, so the weight in pounds of 8 vehicles and the variability of their braking distance measured in feet when stopping on dry surfaces are shown in the table. At a significance level of 0.01, is there enough evidence to conclude that there is a significant linear correlation between the vehicle weight and the variability in braking distance? Okay. So it looks like we got vehicles of various weights and how long it takes for them to stop. Okay. Now, this is a problem where they've told us in there which one they want us to use for X and which one they want us to use for Y, so I'm going to go with it. But I need to take a look at this data and see if it looks reasonably linear, and we'll go from there. Now, I'm going to first start, though, by pulling some information out of there. What's the claim? Well, the claim is a significant linear correlation. So, a significant linear correlation. Doesn't say whether it's positive or negative, just says it's a correlation. So that means when we're taking a look at our null hypothesis and our alternate hypothesis, our null is going to be that rho is equal to 0. Our alternate is going to be rho is not equal to 0. Right? And that claim is going to be the alternate. Right? Our data is that table above, as well as an alpha level of 0.01. All right, first thing I do is I need to get this data into my calculator. So I'm gonna go ahead and do that. I'll pause the video and come back. You don't need to watch me do that. All right, here we are back. Data is in. Remember, anytime we're putting data into the calculator, that's the weak point. So we wanna make sure we check it, maybe check it twice, because that's when things go sideways, right? That's when things end up making mistakes because data's in wrong. All right. I want to point out something else here, and I just noticed it when I was doing this. In the last problem, when we put the data in, someone was kind, and they organized the data so that our x's were always increasing. Right? They didn't do that here, because it goes 48, 56, 58, 59, 53, 65. So it's going up and down. Calculator does not care. Okay? Now I'm going to take a look at the picture. I'm going to look at the graph and see if it's doing what I think it needs to be doing. Remember, back to stat plot, plot 1. Until I turn it off, this is going to stay turned on, and it's always going to make x's list 1 and y's list 2 unless I change it. So all I really need to do every single time is fix my zoom to be, let's see, zoom stat, and then look at the data. Okay, now I got something weird going on here. This data right here looks good. That data point right there doesn't look so good. I wonder what that is. So if I trace it, I can see that's the data point 5340 1.9. I didn't type it in wrong. That's a data point, so it's not a mistake. So I'm going to run with it. Right? Because everything else looks pretty linear, but that one doesn't. But I have no way to know that that's an outlier, so I'm going to run with it, and I'm going to run my hypothesis test, because overall it does look pretty good. So stat, test, lin-reg t-test, and if I don't ever change anything, it'll keep drawing from the right places. That is, it'll draw the x's from list 1, the y's from list 2, it'll set my alternate hypothesis to be not equal to, and it'll calculate. Right? Let's talk about this, though, as long as we're here. Regression equation. Right? Now, the calculator, when it runs this test, finds the equation of the line that should fit through it, that it thinks is the best fit. This command right here that I left blank before, that's asking, do you want to save that anywhere? And what I'd like to do is I would like to put it in Y1 in my graph so that it'll graph it on top of that data. So I'm going to do that. Now, the way that I do that is I'm going to go to my variables, which is right there, down there below the down arrow. I'll scroll over to y variables. I'll select option 1 there, function, and I'll pick y1. And now when it does that, when it runs the calculation, when it runs the test, it'll also store that equation in y1. And I'll show you what I mean here in a second. So I ran this. I've got my t. I've got my standardized test statistic there at 1.94 if I need that. But more importantly, I've got a p-value. And my p-value is 0.09911, blah, 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 blah. Now, when I compare this to my alpha, my p is greater than alpha, right? So I have to, let's see, when p is greater than alpha, I fail to reject the null hypothesis. Since my claim was the alternate, I've got to say that there is not enough. How do you spell enough with a letter past the H? It ends with H. Evidence to support the claim. But I want to, go back and point out something. Remember how this point right here we felt was kind of wonky? What if we went in and deleted that point? What if we could prove somehow that that was an outlier? So if I went back to my stats and edited it, I'm getting rid of the 5340. Is that what it was? Yeah, that one. So I'll just go down to it and press delete. I'm also needing to remove the 1.93, so I'll delete that too. And now if I went back and ran the test again, so boopity 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 boop boop, all the way down, do my calculate. Look at the p-value now. Now the p-value isn't 0.099. Now the p-value would be 0.002, which when I compare, now we would reject the null. So do you see how that 1 point changed this from fail to reject, and removing that 1 point would mean reject? So that's what I was saying earlier when I said that this thing, hypothesis testing on correlation coefficients, is incredibly sensitive to outliers. This data point appears to be an outlier, and if it wasn't there, we would have a significant linear correlation. But because it is there, we don't have a significant linear correlation. Isn't that crazy? 1 point blows the whole thing up. Right? Now, I have no way of knowing whether that point is an outlier or not. I don't have enough information. I mean, honestly, I do. I could run some tests on the data and prove it's an outlier. But again, that's outside the scope of this course. Okay? All right. Moving on, though. Correlation and causation. Right? Now, here's that common phrase that correlation does not imply causation. The fact that two variables are strongly correlated doesn't mean that there's a cause and effect relationship. It just means that you could put a line through it and the line could use one variable to predict the other, but it doesn't mean that one variable is causing the other. Okay? When there is a significant correlation between two variables, some things you should think about is there a direct cause and effect going on here? Does X cause Y? Or is there some sort of reverse relationship where Y causes X? Because if you choose which one is X and which one is Y, maybe you choose wrong. Maybe your independent should be your dependent and your dependent should be the independent. Right? So why is there a relationship? Right? What is going on there? Right? Sometimes weird things can happen where there can be a correlation between two variables, but both of them are being acted on by a third variable. This isn't even showing up in our data, but it's controlling them both, and that's why there's a relationship between them. Right? That sum is referred to as a lurking variable. It's a variable that has an effect on the variables being studied, but we don't really know what it is. Okay? And then there's always the possibility there's just some weird coincidence going on. Okay? All right, so let's take a look at one of those situations. This is the data set. I got this from this guy named Tyler, I think it's Vigan. And he has a website called Spurious Correlations, and that's his website right there. He sells a book. So here's some data. It is the per capita mozzarella cheese consumption. So this is how much mozzarella cheese people eat per person measured in pounds. And civil engineering doctorates awarded. And what I'd like to do is add a 0.02 significance level. Is there enough evidence to conclude that there is a positive linear correlation between the two? Right? So our claim is a positive linear correlation. So then when I set up my hypotheses, my null and my alternate, a positive linear correlation would mean that rho is a positive number greater than 0. The null would then be that rho is 0, that there is no linear correlation. Our claim's the alternate here. I'm going to take this data, I'm going to put it into the calculator, I'm going to call these guys x and these guys y. I'll be right back. All right, I've got the data in. I'm going to take a look at the picture. Remember, since I've set it up, all I have to do is ever zoom back to stat. It looks reasonably straight to me. Let's run the test. linreg t-test, right there. I run the test. My alternate is that it's greater than 0. I calculate, and I get a test statistic of 9.5. I get a p-value of 6.08 times 10 to the negative 6, so that means 0.02345, 5 zeros, 608. My alpha level, 0.02. When I compare p to alpha, p is way less than alpha. That means we reject that null hypothesis, so there is enough evidence to support the claim of a positive linear correlation. So we just statistically proved a relationship, we statistically supported the claim of a positive linear correlation, meaning that if we eat more mozzarella cheese, that will cause more civil engineering doctorates to get awarded, because that's the correlation we just came up with. But there's no way that eating more cheese causes civil engineering doctorates to be awarded. There just has to be some other reason why those two things are correlated. Or maybe, just maybe, it's a coincidence. And so if you have the time and you're feeling bored, go to this site. It's kind of funny. He has found an amazing number of data sets where there's a correlation there, a positive relationship, a statistically supported correlation between data sets that have no reason to be together. Okay? All right, that brings us to the end of section 10.1. We'll come back and take a look at section 10.2 in the next videos. Have a great day.